Okay, so here's our next talk. This is a physics lecture on fluoro. I'll touch on angio a little bit also, since that overlaps. So I want to start out by talking about the differences between what's done with fluoro and what's done with general radiology. So fluoro is different, whereas general radiograph or diagnostic radiograph is a static image. Fluoroscopic imaging is done to view dynamic processes like swallowing or watching blood flow. So what are the actual differences? Well, the difference is that whereas regular X-ray is done with a very high MA and a very short exposure time, the opposite is done in fluoro, where you have a very low MA and a very long exposure time, because you are going to be watching a dynamic thing happen. Now, the reason you have to lower your MA is so that you don't, it reduces the chance of overheating so that it can stay on longer. Additionally, so the images are still performed at a normal KVP, and that is because you still need regular, you still want your regular image contrast. You're not doing mammo. You don't need to use high or very low energy levels. Now, the focal spot for fluoro is relatively smaller. It's not as small as the mammo focal spot, but it is smaller than a regular diagnostic focal spot. And the reason that it's done is to limit geometric blurring. Now, larger focal spot is still used for the spot image, which is basically a regular X-ray, and that's because when you use a regular X-ray, you're using a regular current. So think about a spot like a conventional X-ray. A frame shot or a last image hold is different than that. That's like you're just actually telling the computer to hold the last image that was shown on the fluoro screen. So let's talk about a concept which we mentioned sort of before, which is noise. But I want to talk about it a little more with regard to fluoro. So there's this idea of this entity called quantum model. So what is that? Well, basically, you've got a concentration of X-ray photons that are used to produce an image. The more photons you have, the less background noise that's sort of existing. So more photons, less noise. To get into actually what quantum model is like a super complicated calculus lesson, so we're not going to do that. But let's just say that it's a statistical fluctuation or standard deviation in the quanta of photons that are absorbed per unit size by the screen. The bottom line is that if you increase the number of photons, in other words, if you increase your MA, you can decrease your model, because there is still a statistical fluctuation, but you're drowning it out by making it less and less and less significant. Increasing the KVP will not help. In fact, that can actually increase the model. So KVP can make it worse if it's done alone. If you're having a patient, if you've got a gigantic fat person and you are photon starved, which is when you tend to see quantum model, you need to turn up the MA, not necessarily the KVP. In fact, that can make it worse. So there's two main types of fluoro systems. There's the IIs, or the image intensifiers, and this is sort of old school. And then there's flat panel detectors, which are the newer ones. So let's start out talking about just sort of the general setup of how a fluoro table is set up. You have the X-ray tube underneath of the patient, usually. There are a few exceptions, but let's just think about it like this. General X-ray tube underneath of the table, and then you have a beam that's typically collimated, and then goes through the patient, and of course there'd be some scatter because it's Compton scattering as it goes through the patient, and then you have a grid to address that, and then that hits into an image intensifier. So what is this image intensifier? basically, it converts the X-rays to electrons, then it accelerates those electrons, and then it converts that to a visible image. So something like this. So you've got this cesium iodine, which is the input phosphor. That's going to capture the X-rays and turn them into light. Okay, and then you're going to want to turn the light into electrons, which are then accelerated over a gap, and that's that will be referred to as a flux gain. Really, it's not super important. And then that will hit on the output phosphor, which turns the electrons back to light. So that process there is referred to as a minification gain. So what does that mean? Basically means that you had a large photocathode surface originally, and you then concentrate them on a smaller output phosphor. So you've got an increase in the number of electrons per unit area, and therefore the energy per unit area. So the number one take-home message here is, what are you doing when you're actually magging something? You are minifying it less. So maybe something like this, where you're not minifying it as much. All right, so let's talk. So now that I've brought up this concept of magnification, let's talk about the different types. There are two different kinds, and they are highly testable, to be made interchangeable for the purposes of confusing you. So there's geometric magnification, which is the one that you're more familiar with from prior lectures, even though I don't think I called it that, but now I'm going to. And then there's electronic mag, or the zoom. So let's talk about geometric mag first. It's basically this idea that if you put the object closer to the source, that is going to result in an increase in magnification. So to mag something, you bring it closer to the object source, and you could draw this out like we did in prior lectures to prove that to yourself. Now, people usually think about the inverse square law for reducing radiation, but obviously it works the other way too. If you get closer to the tube, you're going to get more radiation, and it doesn't double, it squares, because it's an inverse square law. So this is not really a good way to magnify something. So, summarizing, you bring the object closer to the source, and it will magnify it, but it results in an increase in radiation that's not doubled, that's squared. Now let's compare that to the electronic mag. So if you decrease the input field of view, then you're also going to be decreasing how much actually comes out. Now this is going to result in a brightness decrease because you've reduced the amount that's actually coming through here. So that does actually, you do have to pay a penalty for that. Your choices are to either have an image that's not diagnostic, or you end up increasing the juice. I'll talk about this a little bit more as the talk goes on, but there's this entity called an automatic exposure control, which is like a monkey that sits back here and looks to see if it's bright enough. And if it's not bright enough, it automatically increases the juice. So how much increase? Typically, the dose increases between 1.4 and 2 times for each sort of change in magnification. Now remember, that's less than the inverse square, obviously. So you're talking about getting less increase in dose. Both of them increase the dose, but the geometric mag is more, right? So that's a take-home point here. So both of them increase dose. Geometric mag increases it more. Now let's talk about some things that you can do to reduce the dose. So just to orient you here, we've got this is our source here, the orange one, And so this is our patient or object source distance. And then this is our II. So this is our, object to receptor distance here. So we can manipulate this in a bunch of different ways, right? You could increase this, you could decrease that, you could increase that, you could decrease this, you could increase them both, you could decrease them both. So which one do you think would be the best for reducing dose, optimizing imaging quality, and reducing dose? You just think back to what your fluorostations usually look like, assuming you've got a conventional fluorostation where the source is under the table, like that. So what you want to do is decrease this distance here. You try to bring that thing down right on top of the patient if you can. You want that small. And you want to increase the distance between the source and the patient. Now, having the image intensifier as close to the patient as possible is going to do a couple of things for you. One, it does decrease dose to the patient because you've got the automatic brightness control is trying to make a pretty picture. If you have more X-rays actually being detected because the II is closer, the automatic brightness control is not going to increase the MA as much to make an adequate picture. Two, you've got decreased scatter to the operator. In other words, if you bring that thing down, and with less X-ray scatter, you've got less radiation to you or less radiation to your eyes, etc. And the last thing is that it's actually going to increase the sharpness. All right, so the distance between the tube and the patient is going to the main thing that's going to do is that's going to decrease the dose, right? And it's not going to decrease it by half. It's going to decrease it by a factor of 4 because that's that inverse square law that I keep bringing up. All right, so things you can do to decrease the dose. One, you can bring the patient close to the II and far from the source. That's what we diagrammed out there. That's very important. 2, you can collimate. And 3, you can avoid magnifying if you can help it. Because, like I said, even though the electronic magnifies less than the geometric type, it still increases the dose. Now, some things you can do to increase spatial resolution is basically minify things less. If you think back to that diagram, so magnification will increase the spatial resolution, and collimation will as well. Now, what's the main limiter to spatial resolution? For the old systems, the II systems, it's actually the display TV, how good that display is. That's not the case with flat panel detectors. So, speaking of flat panel detectors, so let's talk about those. So we covered the II. Now let's talk about the flat panel detector. So they work a little bit something like this. So you've got your X-rays coming in here with a grid, and you've got your phosphor, which takes the photons and turns them into light, similar to what the II does. But then you've got the absorbed light converted to electrons, and then you have an immediate readout. So you don't need a television camera, and so you're not limited by that television display. Instead, flat panel detectors are limited by the detector elements, which themselves are around 2.5 to 3 line pairs per millimeter. All right, that's pretty much it. All right, so switching gears gracefully, let's talk about, let's move into the angio suite here just for a few minutes and talk about how that's slightly different than conventional fluoro. So here are the special extras with IR imaging. Because you're trying to visualize really small things like tiny little vessels in real time, you need a very small focal spot and a large number of x-rays. So to deal with a small focal spot, you've got, they end up doing a couple of things. They will add these local heat exchanges onto the system to avoid melting the entire unit. The anode angle is very small when compared to conventional X-ray, and this smaller anode angle leads to an increase in the Heal effect. Unfortunately for IR, the Heal effect pretty much is zero because you're using such a small field of view and a small image detector, which means you're really only looking with the central portion of the X-ray beam to image. Now, the other thing is that it's really important to have that KVP set between 60 and 80 because you want to nail that K edge and really maximize your contrast. A higher KVP is going to lose that iodine contrast. And lastly, and this is, out of all of this, probably the most testable point because it's a safety thing, you don't use a grid for small things. If you remember back from prior talks, I said that you get a bigger body part gives you more scatter and a smaller body part gives you less scatter. So for a body part or body that is less than 10 centimeters, for example, a baby, the grid should not be used. Because remember, the grid increases dose because you've got that Bucky factor and those kinds of things. You're blocking X-rays, so there's going to be less, so you have to turn up the juice to make a good image. So if you're having less scatter, you don't need a grid. Don't use a grid for peds. Don't use a grid for extremities. All right, so let's talk about how DSA runs. So, DSA is, you hear that all the time, digital subtraction angiogram. Essentially, what you do is a masking image is done. That's the first image. And it's going to subtract away anything that's not moving. And then you're going to have the only thing that's left over is the stuff that is moving, i.e. the blood that you've injected contrast in. So that's all you want to see. You just want to see the vessels with the contrast. You don't want to see bones and bowel gas and all that other stuff. That's distracting because you're trying to look at some really tiny stuff and see really subtle blushes and those kinds of things. So that's the reason that it's done like that. So that's why you tell the patient to hold their breath, because you don't want the diaphragm moving. If the diaphragm is moving up and down, you'll end up seeing big black streaks like that. And it's also the reason why you will typically see a little bit of bowel gas on a DSA run, because the bowels, you can't tell them to hold their peristalsis. So probably have a pedal that looks like this in your angio suite. Most of them look the same. This guy here is usually for the overhead light. This is typically to tap the fluoro button. And then you've got something like this that's what you tap on when you want to do your DSA runs, where you step on it and hold it. So here's an example. Notice that the diaphragms are black like this. That's because they are moving just a little bit. And bowel gas is there also. Probably the reason you're seeing these rib shadows like that is because they're moving up and down. Notice you can't see the spine hardly at all, that's been taken out, and that's what it's supposed to do. And then, you can do your run, and that blood is something that's moving, so that then you're going to be able to see it. All right, so let's do a little bit of terminology that's slightly different for angio. So normally the views are defined by the direction of the X-ray beam, but in angio it's a little squirrely, where the terminology that's typically used has to do with what side of the patient the II is on. So, the source is still under the table here, and the II is over here. So over here, this would be an RAO. So it's we've got it's on the patient's right, and anterior, and then over here, this would be an LAO. This is just for IR now. So, where's the best place to stand? Like, where should I stand in the room? And the point, you're going to make this decision assuming that all things are equal for performing the procedure to minimize your Compton scatter. So where you want to stand is on the side of the image receptor. That way you're avoiding the majority of the scatter. So standing over here is the best spot to stand. All right. Actually, the best place to stand is behind your trainee, using them as a shield, and then reaching around them to do the case, because that lead, it's heavy. So as a point of trivia, the dose received, assuming that you're not wearing lead, standing 1 meter from the patient, is about 1/1000th of the dose received by the patient. They also say that to maximize to maximize for this distance here for the patient, remember you want this one big and you want this one small, that if you're short, you should stand on a platform to keep that source to image, the source to image, like you want to maximize that. So you don't want to be like, oh, we got to lower the table because I'm short. You should stand on a platform to keep this distance big. Or you can have your trainee stand on all fours, sort of like a dog, and you can step on their back during the procedure also, if that's more comfortable, or if a platform isn't available. So a little bit on radiation here. I have to define a vocabulary word, which is KERMA, which is an acronym for kinetic energy released per unit mass. KERMA. And there's basically two steps on what's going on when you have energy transferred. These are things that I've sort of mentioned before. The first process is typically energy transferred to a charged particle. So something like that, Compton or photoelectric effect or whatever. And then now you have a charged particle. So the part two is the charged particle transferring energy via excitation or ionization. So that's part one, energy is transferred, and then part two is, either that or something like that. So that's part two. So why do I bother even bringing this up? Because KERMA is step one. Was just that first part, the energy transferred. It's not part two. So if you're dealing with a low energy photon, then your KERMA is going to be the same as your absorbed dose. But if you're dealing with a high energy photon, then the KERMA is actually going to be more than the absorbed dose, because some of these secondary electrons are going to escape the area of interest before depositing their energy. And these are going to be counted in KERMA but not in the absorbed dose. But in general, tissue doses are higher than air KERMA by about 10%. So the sum of kinetic energy of all the charged particles made when an X-ray or a gamma ray passes through a unit of mass air, that right there is an air KERMA. So when you hear the air KERMA was this or that, I mean, it's a idea for defining how much dose the patient's getting. But the physicists who were ever developed it, we're not talking about what's going on inside the patient. This is an air KERMA. It's within a unit of air, a mass of air, the kinetic energy transferred to the charged particles. Remember, just in that first step. Now, another vocabulary word that you hear sometimes is the entrance air KERMA, which is that's the air where the X-ray beam would enter the patient, measured without the patient. So it's measured without the patient. You're not measuring the Compton scatter and all that kind of stuff that goes on there too. So it's air right outside of the patient. The last vocabulary word with regard to this is the KAP, or the Kerma air product, or the air Kerma product. And this is supposed to account for the total amount of radiation on the patient. So it's the entrance air Kerma times the cross-sectional area. Sometimes people will call this the dose area product, something like that. All right, so we'll get into some of the trivia here. It's important to understand that the measurement is independent of the beam location. Now, it's true that as you move the beam away from the patient, the intensity is going to decrease. But as the beam spreads out more, it's actually going to equal out, so that the KAP is not dependent on the location. So, it's spreading out before it, you're losing here, but then it's compensated for the fact that you're losing here, and that's in the same amount. So here's a take-home point: highly testable. It's independent of the source distance. Another thing that's important to understand is that low dose to a large skin area and high dose to a small skin area is the same because of that calculation. Remember how that formula is actually done, or it's, your dose versus times your surface area. Magnification will increase the air Kerma, but not the air Kerma product, or the KAP. Obviously, this doesn't help you grade your risk of a skin burn. Instead, it's used to estimate sort of total energy deposited in a patient, effective dose, cancer risk. Sometimes, if something reduces the risk of the KAP, it probably also reduces the scatter, and it probably also reduces the patient's dose. So generally, it's not totally useless. Just remember how that formula is calculated, and remember that the distance doesn't matter. All right, so if you look up at your monitor when you're in the angio suite, typically there's something like this, usually up on one of the screens, and that air Kerma is this one here. That's the thing that's actually on the monitor, and pretty much everywhere. It's like a regulation. Also, the cumulative skin dose is typically kept also because to keep track, the radiation physicists keep track of this stuff. You need to know whether or not you're going to burn somebody. Like if you're, for example, if you're doing a TACE or something like that, you're supposed to, or any kind of long procedure, you're supposed to sort of move things around in there a little bit, like this. Like if you can get a little bit of, you can still see what you're doing. You don't want to just leave it in the same spot the entire time. And this is called dose spreading. It's a strategy that's recommended, and it's a vocabulary word worth knowing. So that's what dose spreading is. It's just sort of moving your image, your X-ray generator around, moving your source around so that you're not burning on the same spot. Like, I mentioned before, let's say that you're doing a TACE on somebody, you don't want to put a big burn on the left side of their back. Boom. They don't like that, and they probably will sue you for it or try to. And you may be thinking to yourself, why would it be on the left side of the back? I thought that the liver's on the right side. That's true, but remember how we name these things. So the II is on the right side of the patient, and we're imaging through to get to the liver over here. So this is where the skin gets burned, is right at the entry site. So just as a general idea, below 2 gray, you're probably going to be okay. Between 2 and 5 gray, You may very well have burned your patient, and you have to look out for that, especially around 10 days post-procedure. And if you happen to give somebody more than 5 gray, well, then you're going to end up getting reviewed by the physics department. All right, so that's the end of this talk.